An autonomous AI agent tasked with credit adjustments reviews a vendor portfolio. Within milliseconds, it zeroes out active credit lines across 40 accounts, the logs, expecting to find a model hallucination or a glitch in reasoning. Instead, they find a model that functioned exactly as programmed. Forensic logs show the model successfully processed every available parameter. It simply relied on a stale bankruptcy flag that had been superseded hours earlier. The machine made a perfect decision based on the wrong reality. When autonomous systems fail at scale, the root cause usually originates in the hidden data infrastructure feeding the model, rather than the model itself. For 30 years, enterprise data architecture has been organized around a single principle. Humans ask the questions. A person submits a query, waits for the dashboard to load, and decides what to do next. This animated diagram compares that traditional model with the new reality of agentic AI. On the left, the slow, cyclical human workflow. On the right, a machine consumer that requires context in sub-milliseconds and acts instantly, entirely on its own. Wiring a hyper-fast autonomous machine into an enterprise data lake designed to update once a day creates severe mechanical friction. The agent needs to update its working memory mid-task and make cascading decisions, while the database is still running slow batch jobs. An agent making decisions in seconds cannot wait for a data lake that only refreshes every 24 hours. This latency gap creates a state of permanent misalignment, forcing the machine to act on information that is effectively expired. To understand why this happens, we have to look at how these agents actually pull information. The friction starts at the retrieval layer. Standard flat search methods, like basic vector retrieval, are designed to find documents containing related keywords. That works for a search engine, but an agent needs to evaluate causal relationships to execute a multi-step workflow. This diagram shows what reasoning actually requires. An agent needs a knowledge graph, a highly structured web of connections that tells it who reports to whom, what dependencies exist, and why specific rules apply to specific accounts. Even if you build that graph, feeding it with a traditional enterprise data lake means operating with a 24 to 48-hour lag. A human analyst knows to check timestamps. An autonomous agent takes yesterday's data as absolute truth, acting in real time. This creates an immediate governance crisis. An agent might touch 47 different data sources in 3 seconds to complete a single task. Traditional audit trails, built to trace an analyst's occasional query, capture none of this reasoning logic. Slat retrieval methods, stale update schedules, and broken audit trails combine to make standard enterprise data toxic for autonomous decision-making. Because agents execute without human review, these architectural gaps turn into silent errors that spread quickly through downstream systems, completely evading standard software alerts. We see this first as stale context poisoning. A customer's financial status changes materially overnight, but the agent accesses a lagging data warehouse and executes a binding financial contract based on a reality that no longer exists. This diagram illustrates another failure mode, vector drift. The underlying company policy has changed, but the system reports high confidence because the semantic keywords still match. The agent receives authoritative-looking context that is entirely factually wrong. The most persistent threat is memory poisoning. A single corrupted node or false relationship injected into the agent's long-term knowledge graph permanently skews its understanding of the business, corrupting every future decision that touches those entities. These specific failures are the inevitable outcome of a design gap between how machines consume data and how humans store it. No software patch can resolve a conflict built into the architecture itself. Ripping out decades of enterprise data infrastructure is not a viable option. Companies have billions of dollars tied up in their current cloud data warehouses. Attempting to retroactively re-engineer every historical record and archival table to operate at sub-millisecond agentic speed would be an impossible, cost-prohibitive project. Survival requires a bifurcated strategy. You accept the legacy system for your human analysts, and you build a highly targeted parallel track specifically for your machines. The knowledge lake is a high-speed, semantic nervous system built atop your data warehouse. You leave vast, raw historical data in the legacy stack for human reporting. Instead, you extract the critical 5% of high-signal data, modeling it into a real-time causal graph purely for AI. Isolating this small sliver gives autonomous agents the precise relational context and sub-second freshness needed to act safely without disrupting broader enterprise operations. Competitive advantage in the next decade shifts from the raw power of the AI model to the integrity of the data stack. The most capable agents will be the ones supported by high-speed, relational foundations built specifically for their needs.